This one is going to be 5.7, which is enthalpies of formation. And this is really just kind of an extension of Hess's law. This is taking way longer than if I had just written delta H.
Is that what delta H stands for?
Enthalpy is delta H. Yeah. So this is the section, and a couple of basic things you need to know from this. First of all, delta H of formation, the way that we write that is delta H with a little f down here. I told you, we put all kinds of stuff as subscripts on those delta H's, right? They can be almost anything. Well, I can't think of anything that it can't be, really. Something that doesn't have a delta H, but everything can have a delta H, right? Because pretty much everything that's matter can have heat transferred to it or away from it, so you can have a delta H for it. So, yeah, just try to think of it. All right, so the enthalpies of formation, what that means is, it's basically, and let me look at the book definition to make sure that I get this. Okay, for the formation of a compound from its constituent elements. All right. Now, that's not complete because it's the formation of 1 mole of a compound. All right. So if I want to know the delta H of formation for CO2, then the heat of formation for that would have to be carbon plus oxygen yielding CO2. Okay, and whatever the delta H is for that reaction, that's the heat of formation for carbon dioxide. Does that make sense? You're just taking whatever's there, and you think about, okay, so this has carbon, this has oxygen in it. So the heat of formation reaction for that one would be carbon plus oxygen yielding CO2. All right? And that is the heat of formation for CO2. Now, if you get enough of these, then you have this, pretty soon you have this big long table of heats of formation for all of these different compounds. All right? And you can basically use these heats of formations as one more way to calculate the delta H of a reaction. Okay? And so, I guess, let's look at sample exercise 5.10, 5.10 for a second. Just to kind of talk through that idea. Because all they're doing here, oh sorry, that's on page 190. Page 190 in the book. There's one up here if you want it. So it's basically asking here, for which of the following reactions at 25 degrees Celsius would the enthalpy change represent a standard heat of formation, or enthalpy of formation? And for each one that doesn't, what changes are needed to make it an equation whose delta H is an enthalpy of formation? Now, it might be helpful while we're going through these if you just kind of cover up the solution somehow. I've forgotten to say that because I know the solution is right below it, but if you kind of listen to my explanation of it, you might get a little more out of it because it's going to be sequential. I mean, there's a sequential too, but sometimes I say words differently than they say words. So it might make more sense when I say it. So for letter A here, if you're looking at this, we've got 2 Na solid plus 190, yeah. 1/2 O2 gas yields Na2O solid. Okay, so for it to be a heat of formation problem, what are the requirements? Okay, now this is going to throw some of you off, right? A 1/2 coefficient here, but we'll talk about why that's a 1/2 in just a second. I didn't teach you about half coefficients last year because I thought that would have confused some of you. The only time you'll really ever see it in chemistry is when we're talking about thermochemical equations, like we're talking about right now. Then you might see halves. Now, when you go and practice some of the Hess's law stuff that we talked about the other day, you're going to notice some halves on some of those equations as well. Okay. But remember, the requirements for it to be a heat of formation reaction is it has to start with its constituent elements. In other words, the elements that it is made of, right? So Na2O is made up of sodium and oxygen, right? Is this sodium in its elemental form? This is oxygen in its elemental form, right? So that requirement is kept. Now the other requirement for it to be a delta H formation, a heat of formation, is that you need to only form 1 mole of the product. Did we only form 1 mole of the product? Yeah, we did. Now, here's why. This is actually the answer to the question, Jennifer, why we use the half coefficient right here. When you normally balance this thing, oh, okay. There'd normally be a 4 here. It would normally look like that, right? So that would be a balanced equation. But that forms 2 moles of the product. So we'd have to double the heat of formation, right? So if we want it to be a heat of formation reaction, you're adding 2 moles of Na plus half a mole of O2. And that's totally fine. That's just half of 6.02 times 10 to the 23rd, right? Which we can do that. And then this is going to end up just being 1 mole then at the end. Okay? So that's why we use the half coefficient on that one. All right, looking at letter B, 2 potassiums, liquid, plus Cl2, gas, yields 2 KCl solid. Is that a heat of formation reaction? Why not? Okay, we're forming 2 moles of the product. Now there's actually another reason as well. Is a liquid, is that potassium's most natural state? Now it's a metal. Its most natural state is a solid, right? So if this was potassium solid combined with chlorine gas to form 1 mole of KCl, then it would work, okay? And what we'd have to do here is take away this 2 in front of the K. I don't feel like erasing, so I'm just going to scratch it out. Put a 1/2 here in front of the Cl2. And then scratch this out. And then change this to a, so need to be changed to a solid. Okay, and once we did that, that would be a heat of formation reaction. Okay? And then the last one, C6H12O6. Solid yields, I want to know how to do this reaction. 6 carbon diamond. We're breaking apart sugar and getting diamond. Plus 6H2 gas plus 3O2 gas.
Why?
All right, so heat of formation reaction or not?
No.
No, there's all kinds of problems with this one. What's the first problem? Well, yeah, I guess, I mean, really, this is kind of the compound we should be focused on, right? Which is weird because it's on the left side. That's a problem. Okay, so this isn't a heat of formation. This is a heat of decomposition, right? Because you've got something breaking down into its constituent elements. So if we flip-flop this thing, would it be a heat of formation then? We're closer, right? But what's wrong with this one if we flip it? Probably the diamond part. Is that the most natural occurring form of carbon? Okay, so probably carbon as graphite would be more reasonable here, right? So if we flip this thing around so that the reactants were on the product side and the products were on the reactant side, then we would be making 1 mole of the product, right? And then if we change that diamond into graphite, then that would be a good heat of formation reaction. Okay? You guys kind of see how that works? All right, so that's heat of formation. Now, you can actually use those heats of formation And if you want to read in the book, they do a good job of showing how Hess's law really is what causes this this equation to work. Okay, but ultimately, what you need to remember is if you take the heat of formation, I guess it's the sum of the heat of formation of the product. Just whistled. You guys know what I mean when I write this? Sigma, sum. It means you take the sum of all of the product's heats of formation, and you subtract the sum of the heats of formation for the reactants. And that's going to give you the overall delta H for a reaction. Okay? Now I guess the other thing that they put in that equation, they put an N right here, and they put an M right here, I think. And those just stand for the number of moles for the coefficients, basically, in the equation. All right? This will make more sense once I show you how to work one of these. But basically, you're using this equation to figure out it's another way to figure out the heat of reaction. Okay? So look at sample exercise 5.11 on page 192. We'll run through that one real quick. Hopefully real quick. So calculate the standard enthalpy change for the combustion of 1 mole of benzene to form CO2 and H2O. All right, so here we've got, we probably need to write a chemical reaction first, right? An equation. So we've got C6H6. And is that liquid? Yeah. So when it combusts, what does it have to react with? It has to react with oxygen. So plus O2 yields CO2 plus H2O. That's our typical combustion reaction, right? And they're asking us, what is the delta H for this reaction? Okay. We probably need to balance this. So if I put a 6 in front of the CO2, what else do I need to do? Is it okay if I put a 3 here? That's going to give me an odd number of oxygens, right? So I probably want to double this and then put a 12 in front of the CO2. Do they have it that way in the book?
Well,
They have the actual balanced equation?
they have like a 15 over 2 in front of the O2, and then the 3 in front of the H2O.
Well, I could cheat, or I could show you how this works. That's going to sound harsh on the video. I didn't mean for that to sound harsh.
That did sound hard.
Sorry. All right, so then we end up with 24, 30 oxygens, so then you need a 15 in front of the O2. All right? So there's your coefficients for that reaction. And they don't really give us any other information, right? Except for they're planning on you using a table that you can find on page 189 that gives the standard heats of formations for some different substances at 298 Kelvin. Now the other thing I guess I should say here, standard enthalpy. I put a little degree sign up here. That means standard. Standard just means it's at 298 K, which is the same thing as 25 degrees Celsius. And it's at 1 atmosphere of pressure. Those are standard conditions. Okay. So if they're asking us for the standard enthalpy change, they're asking us at 298 degrees Kelvin. 298 Kelvin, you shouldn't say degrees. So if you look back at page 189 on table 5.3, it gives you the heats of formation of several of these things. So what we have to do here is take the heat of formation of the products, subtract the heat of formation of the reactants, and that will give us the overall delta H for the reaction. Okay. So what's the delta H? I guess I should have labeled the states of matter here because it actually does matter. I wasn't being funny. Don't laugh at that. Sorry, that sounded harsh too.
So mean today.
CO2, this is gas, this is liquid, this is gas, and the C6H6 is liquid, okay? Because you do need to know the states of matter because it does make a difference as far as the delta H value that you get, okay? All right, so we need to look up the delta H of formation for CO2, which is what? For CO2 gas. Negative 393.5, okay? So what I always like to do is kind of bracket this whole thing. So the delta H of the reaction here is going to be equal to negative 393.5. Now notice the units on these. These are all kilojoules per mole, right? Okay. So I have to multiply it by 12 because there are 12 moles of carbon dioxide in this reaction, right? So I have to get rid of that mole part. Usually need a lot of room for these, okay? And then I'm going to add that to the other product that I have, which is my H2O, which this is H2O liquid, not H2O gas, so that's important because it's a different number. Negative 285.8. Kilojoules per mole times 6 moles, right? Okay, so there's my reactant, or sorry, my product side. So I need to take products minus reactants. Okay. Now let's look at the C6H6 liquid. That's benzene, and that's 49.0 kilojoules per mole. That's a positive number. You got to watch your signs on these. That signs can kill you on these problems. 49.0 kilojoules per mole times 2. Okay, and then we would want to add the oxygen to that. But I don't see oxygen on this list. Do you? Okay. So another thing that we haven't talked about yet is that anytime you have just an element that is in its normal, natural state, we're going to give that a delta H of formation of 0. Okay? Because since that's the most natural state for it to occur in, we'll just say its heat of formation is actually 0. And anytime it reacts and does something else, we would give it a heat of formation. Okay? So because that's 0, we actually just need to add this part to 0, so we can just kind of in our brackets here. All right? So then all you have to do is work this all out and make sure you keep your signs correct. Negative 393.5 times 12 plus negative 285.8 times 6. And then all of that needs to be subtracted from, or no, not subtracted from, you just subtract from that the 49.0 times 2. And so I'm ending up with, double check my answer to make sure I didn't miscalculate here. Negative, I did miscalculate. What did I do? They balanced it differently, but it shouldn't have made a difference. They just didn't multiply by 2 at the end. Oh, wasn't paying attention. Okay, so I got the right number here. You should have gotten a negative 6534.8. Is that what you guys were getting, or did you even calculate it? Okay, so negative 6534.8. But what I wasn't paying attention to here was the fact that they are asking for the combustion of 1 mole of C6H6. Okay, when I balance this, that's for 2 moles, so you have to divide this number by 2 at the end, and that'll give you the combustion, or the delta H of combustion for 1 mole. So it ended up being negative, let's do the right fix here, 3267 energy, right? Kilojoules. Okay? And that is how you use the delta H's of formation to calculate the delta H of a reaction. Okay? I think that's about as far as we're going to make it today, but there's really not much else to this section than that. So if you know how to do those types of calculations, that's gonna be the bulk of the section. Okay? All right. See you in class tomorrow.